start recording. So now here is a general organization of a cache. Can you see the general organization of a cache? So in the general organization of cache, how many, and we can partition this main memory address field into 3 bits, namely the tag bits, then the index field, which is k, and the b bits. How many sets are there in cache? Yes, how many sets should be in there in the cache? I just wanted to. How many
2 to
sets
the
will be there?
power k.
Anyone? 2 to the power k. So the memory address is partitioned into 3 fields. So it is actually 2 to the power k sets. Okay. The sets, can you see? The set starts from set 0, set 1 until set s. There are s sets. Okay. Each sets has how many ways are there in each sets? Yes. How many ways in this particular example?
The lines.
Yes, the lines are the ways. We also call this as the line or way, it doesn't matter. Okay, so this is 2 sets. There are a ways. We also call this as way or line. So there are a ways here. Each set consists of a ways. And if you look at here, each way holds some fields, which is the valid bit. The bit indicates it whether it contains a valid data or not, and the tag field, which is actually it stores the tag of the main memory block address. And then we have the block data field. How many bytes will be in their block data field? Can anyone tell me how many bytes will be in the block data field? Help me. How many bytes will be there?
B.
Can anyone? Hmm?
2 to the power b.
2 to the power b. Yes. So it contains d is equal to 2 to the power b bytes per cache block. So we start from these are the tag bits, and this is byte 0, and then byte d minus 1. Please. So now this is the cache size, which is actually s multiplied by a. A is the number of ways, and d is now there are d bytes within the block size. Okay. Now this is a simple example. So now this is actually in this particular example. So now in this particular example, we have k is equal to 2. So there will be 4 sets. Therefore, set 0, set 1, set 2, set 3. And there are 2 ways per cache set. And then there are t bits required per way. And there are 2 bytes per way. So the block size is now 4 bits. Okay. So now we need to answer 2 questions. This is very important. So how do we know if a data item, for instance, a particular byte is in memory, is in cache? These are 2 fundamental questions. And then if it is, how do we know if a data item, maybe there's any particular item, byte in memory, is it in the cache or not? And the second question is if it is in the cache, how do we find it? So can you see here now again? Now I'm going to the same thing. So now can you see here how many sets are there? There are 2 to the power k sets, because now it depends on k. And how many ways are there per set? So there are a ways per set. So this is way 0, way 1, and blah blah blah, and p. And how many ways are there? So these are a ways per cache set. Okay. Okay, now the set index. Can you see here? The set index field is used to index into a particular set J. So this set J depends on the set index field. Okay, now the set index field will be used to access a particular set J. Okay, and this set J depends on the set index field. Okay, so the set index field is used to index a particular set J. And what is the range for J? So please look at here. Now this is my J. So this J, the range for J start from 0 till s minus 1. So the set index field is used to index a particular set J, and the range of this J is start from 0 to s minus 1. Okay, and this will tell to which particular set this particular byte belongs to. Any question? Okay, now then what we do? Now we have the tag. Now the tag. So we compare this tag of the incoming byte. So the tag field of the incoming byte address, which is called as tag in, is compared with all of the stored tag. So it is compared with the tag of way 0, it is compared with the tag of way 1, and it is also compared with the tag of way p. So how many tag comparison will be there? Anyone may answer. How many tag comparison will be there? Anyone may answer this question. How many tag comparison will be there?
A.
Yes, very good. A tag comparison will be made. And it is okay. Can you see here? And now can you see here? Now let us assume that the tag of the incoming byte, that is tag in. Let's assume this tag matches with the tag of way P. I call this as tag P. This is now tag P. If this tag of incoming matches with this tag P and the valid bit is 1, so this valid P is 1, both conditions should match. Okay, now what is the range for P now? What is the range for P? So the range for P is the possible value of P is set from 0 to a minus 1. Okay, because now there are a ways. Okay, now if the tag of the way P, which I call as tag P, matches with the incoming tag and the valid bit is 1, it means that now there is a hit. Now it means that there is a hit in way P of set J. So can you see here? So now can you see here? It means that now there is a hit in way P of set J. Any question? Should we proceed? Yes or no?
Yes.
Okay. Now,
Yes.
and then what does the B bits tells me? That B bits. Okay, can you see here now? How many bytes are there in a particular block? There are D raised to power. So there are D is equal to 2 for B bytes per cache block. So these are 2 for B bytes per cache block, and the offset field will access a particular byte M within that block. And what is the range for M? Can you tell me the range for M? Anyone may answer, please. What is the range for M? What will be the range for M? Please, anyone may answer. No, the range. The possible values for M. It may be byte 0, it may be byte 1, and blah, blah, blah. So the range of this M will be from 0 to D minus 1. It can have any value. It can have any value from 0 to D minus 1. Any question? Got it? So offset field is used to index a particular byte M, and the range for byte M is from 0 smaller or equal to M smaller D. Got it or not got it? Any question? Got it? Okay, now we will explain this with an example. So now here, now we have in this example, so now let's assume this is okay. If you look at here, if you convert this number 100 and 10 and 01, it is actually byte number 137 in memory. So can you see this is byte 137? Okay, to which set it is mapped? It is mapped to set number 2. Because how do we know it? Because it is the index field is 10, and 10 is actually the set number 2. So we access set number 2 and we compare this incoming tag. So now this is my incoming tag, which is actually 100. It is compared with the tag of way 0 and the tag of way 1. So it is compared with the tag of way 0 and the tag of way 1. And now we also so if this tag now matches with the second tag. So it means it now in the valid bit. The valid bit of the second way is now 1, so it means that now there is a hit in way 1. So if there is a hit in way 1, so which byte we will access is now the byte offset field. Okay, so this is 0 1, so we are accessing the byte 1 of way 1. So now we are accessing the byte 1 of way 1. Any question? Any question? Should we proceed?
Yes.
Okay, now this is another example. Should we proceed? Any question? Please answer. Any question? Should we proceed?
Yes, clear.
Good. Okay. Now this is another example. Now in this example, how many bits are dedicated for the bytes here? How many bits are dedicated for the bytes here? Everyone is shown here. How many bits are dedicated for the byte address? How many bits?
18.
18. Very good. There's 18 bits. Okay. How many bits are reserved for the tag field? How many bits for the tag field?
7.
7. Okay. The set index field is 5 bits. The block offset field is 6 bits. Okay. How many sets will be there in the cache now? How many sets will be there in the cache?
32.
Yes. Why 32? It is actually 2 to the power 5. So this will be 2 to the power 5, which is actually 32 sets. Now in this example, there are 32 sets. And how many ways are there per set? How many ways are there per set? How many ways are there per set in this example?
Is it 4?
Yes, there are 4 ways. This is way 0. Very good. Way 0, way 1, way 2, and way 3. There are 4 ways. Way 0, way 1, way 2, and way 3. Okay. How many bytes are there per block? How many bytes are there per block?
2 to the power 6.
2 to the power 6, because you know the B field is now 6. Can you see here? So now we have 2 to the power 5 sets in the cache. There are 4 ways per cache set, and then the tag bits, there are 7 bits for the tag bits, and now there are 64 bytes per ways. Can you see what is now the cache size? The cache size is now calculated as S multiplied by A multiplied by D. What is S? S is now 32. There are 4 ways, there are 4s, and there are 64 bytes. 64 bytes. So the total cache size is now 32 multiplied by 4 multiplied by 64 is 8192 bytes, and if we convert it into kilobytes, it is actually 8 kilobytes. And what is now the memory size? Please remember, now the memory size is equal to 2 to the power M. This is 2 to the power 18. This is 256 kilobytes. And now the cache size is smaller than the memory size. Got it or not got it? So the cache size is smaller. Okay. Can you see here now? Now there are actually 64 byte per space. Okay, now the set index field is used to index a particular set. Okay, now can you see here the set index field? So this set index field is now 0001. So this will map to set number 1. So we access set number 1. Okay, okay. Now we compare this tag. Can you see? We compare this incoming tag. What is this incoming tag? 000111. How many comparison we need to do in this set number 1? How many comparison do we need to do? Please answer me. How many comparison do we need? Anyone may answer. Please speak in mic. How many comparison do we need? Please help me. Yasir?
Is it 63?
No. This is because we need to compare the tag. We need to compare this tag. This is tag. How many comparisons? We need to compare it with
minus 1?
No, we need to compare it. We need 4 tag comparison. We need to compare it with the tag of A0, the tag of A1, the tag of A2, and the tag of A3. You got it? And in general, how many tag comparison we need? How many tag comparison we need?
The lines only?
So yes, in general, we need to a tag comparison because okay. Now please remember, this is a so okay. So we can say we need 4 7-bit comparators. Got it or not? Got it? Why? Because in general we can say we need 4 7-bit comparator. In general we can say we need a t-bit comparators. Any question? Got it or not? Got it?
Clear.
Okay, now we need to now if you look at the tag of the incoming block and we need to compare to which line, to which way it is hit, way 0, way 1, way 2, or way 3. Anyone may answer in this example. So now we are comparing this incoming tag. This is my incoming. I'm comparing with tag of A0, tag of A1, tag of A2, and tag of which one is a match? The first way 2. So this is it. So now there is a hit here. So the block, now this block, so to the block to which this byte belongs is now present in way 2. Okay, now we need to access the byte. Which byte we need to access? Which byte of this block? Can you not tell me? Can you not
byte 4.
Byte 4. So can you see here? Now we are accessing byte 4 of the third way in set 1, which is actually way 2. Any question? And this is actually the byte 4. It is actually the 5th byte because the index starts from 0. Any question? Should we proceed? This is all clear or not clear?
Clear.
Clear. So now the cache data mapping determine how a particular data item from memory is met to a specific location. Can you see here? And yes, we did it. Yes. Okay. Now this is a little. I'm now going to elaborate it further. Okay. I also explained it in my first lecture, but I'm going to elaborate it further because I'm going to repeat it. So what is the cache data mapping? So that cache data mapping determines how a particular data item, for instance, a particular byte from main memory is mapped to a specific location, to which SAT and to which way within that set we need to know that. Okay, so now in this case, so can you see here? Now this is now my the byte. This is now my the byte address, and the byte address now consists of 8 bits. Okay, can you see here? Okay, now how do we know that to which main memory block is to which it's mapped? So we concatenate the t bits and the k bits. When we concatenate the t bits and the k bits, it represents the main memory block number. So if we concatenate the t bits, what is the t bits? It's a 4-bit. Here it's this. This is actually 1000, and the index bit, which is actually 10. Okay, can you see here? Now this is actually the address. Please remember this byte number. So what is now? This is actually byte number 137. This is now byte number 137. So this byte number 137 belongs to main memory block 34. And main memory block 34 consists of 4 bytes. Byte 136, byte 137, byte 138, and byte 139. And how do we know the block number? So the block number is determined by concatenating the t bits and the k bits. So when we concatenate the t bits and the k bits, it will give us the block number. So if we convert this number 100, so if we convert 10010, it will give us 34, and it will give us the memory block number. Any question? Got it or not got it? Okay. Now can you see here? Now the set index field indicate to which set this it belongs. So the set index is 1 0. So if we convert this into decimal, it is 2. It means it is now belong to set number 2. And can you see here now the block of set field indicates which byte number within the block. So this byte 136 is byte 0, byte 137 is byte number 1. It means that we are accessing the second byte of this main memory block. Any question? Any question? Got it or not got it?
Got it, Professor.
Good, very good. Thank you very much for a very quick answer. Okay, now can you see here? Now can you see here this 0 1? If you look at this 0 1, this 0 1 it will tell me the byte number, and this byte number is actually byte number 1 in this example. Any question? Okay, now the tag field. The tag field determine whether. Okay, please remember now we are looking at the tag field. Now the tag field will determine whether this main memory block 34, now because this is now main memory block 34, whether this memory block 34 is present in set 2, and by comparing it with the stored tag field, so comparing with all the stored tag field, that whether it's a hit or not. And for determining the hit, we're not only comparing all of the tag field, but we're also looking at its valid bit. So if the valid bit is 1, and if this incoming tag matches with any of the stored tag field, then there will be a hit in that particular way. Any question? Any question? Should we proceed now? Yes or no? Good, very good. So this is in this example. Okay, now in this example, how many memory blocks are there? There are 64 memory blocks, and there are 2 spot 2. And the next slide, how individual block is mapped to a particular set. So can you see here? This is another take by making example. Block 0 is mapped here, 1 is mapped here, 2 is mapped here, 3 is mapped here, 4, 5, 6, and 7 is here. Okay, main memory block 32 is mapped to set 0, 33 is mapped to set 1, and blah blah blah. Got it or not got it? Okay, how many main memory blocks? So please remember, what are the T bits now here? Can you see here? The T bits are now 4 bits per way. These are 4 bits per way. So how many blocks can be mapped to a particular cache set? So there are 2 for T, which is actually 2 for 16 memory blocks can be mapped to a particular cache set, and only how many of them can reside? Only 2 of them can reside at the same time. Okay, so let's assume if you look at to set number 2, which blocks are mapped to set 2? So the blocks that are mapped to set 2 are MB2, MB6, MB10, MB14, MB18, MB22, MB26, MB30, and MB34. Please remember, these are all the blocks, and so far so on. So and this blocks. So there are 16 memory blocks and can be mapped to a particular set. What will be the tag of the MB2? The tag will be 0. It is 0, 0, 0, 0. What will be the tag for MB6? Help me. Yes, anyone may answer, please. What will be the tag of MB6? Anyone may answer. Yes, please go ahead. Yasir.
1001.
0001. What will be the tag for MB10? What will be the tag for MB10? It's not shown here, but what will be the tag for MB10? The tag for MB10 will be 0010. Yes. What will the tag for MB14? The tag for MB14 will be 0011, and so forth, so on. And using the same thing. So what will be the tag for MB34? The tag for MB34 is actually 1000. And what will be the tag for MB64? Anyone? 62. Anyone may answer. Of the last block. Can anyone tell me, please? Anyone may answer, please. So it will be 1111 because you know, yes, 1111, and this is the tag 14. And how many blocks can be mapped to a particular cache set? It is actually 2 for T. And what is T here? T is now 4. 2 for 4. It is actually 16. So in 16, so the minimum tag bits will be 0000, and the maximum tag bit is 1111. Any question? Okay, using the same thing, what will be the tag for MB61 for set 1? So the tag for MB61 will be 1111. The tag for MB33 will be 1000. And what will be the tag for MB5? The tag for MB5 will be 0001. The same thing. Got it? Because they are mapped to different sets. Any question? Should we proceed?
Yes.
Yes, Professor.
Yeah. What will be the tag for MB60? Anyone may answer. What will be the tag for MB60? Can anyone tell me?
1111.
Very good. Very good. What will be the tag for MB4?
0001.
Okay. What will be the tag for MB9? MB9 is not shown here, but I'm just asking.
Tag number 2. 0010.
Yes, 0010. That's, and basically, if you convert MB9, so basically it is actually the tag for MB9 will be 0010. Any question? Any question? Got it? Should we proceed?
Yes.
Okay. Now, and then there is the same thing. So this is actually, and we did it. So byte. Please remember, in the previous case, we say okay, byte number 137 belong to block 132, and then can you see here? This is the set index. This is the compare the tag field, and this found in the cache, and we access. So this. Okay. Now, this is the most simplest form. This is the most simplest form of a cache is called as direct map cache. The most simplest form of a cache is called as direct map cache. And in direct map cache, there is only one cache line. Okay, now if you look at the, if you look at here, if you look at here, from here and from here, okay, look at this figure. How many blocks are there in main memory? Look at how many blocks are there in main memory. Can you tell me? Anyone may answer. How many blocks are there in main memory? Look at this figure, please.
15. 16.
Very good.
16.
Yes. So there are 16 blocks. So basically, the block address starts from 0 and it ends in 15. So there are 16 blocks in memory. How many sets are there in cache? In this example, how many sets are there in cache? Anyone may help?
4.
4.
4 sets. Start from set. Okay. How many ways are there per cache set? How many ways are there per cache set?
Is it only one?
Only one way. Very good. There is only one way. Okay. Okay. Now, can you see here? Now there are calls. So direct map cache is the simplest approach. Each memory maps to a single cache line. For the right on the memory side, it consists of 4 cache sets, and each set has a single cache line or a single cache way. So, okay. Now, which block, which memory location will be mapped to set 0? Which blocks will be mapped to set 0? Anyone may help? Yes. Which block will be mapped to set 0?
0, 4,
4, 8, and 12 will be mapped to set 0. Okay. Which blocks will be mapped to set number 1? Can anyone tell me? Yes. Anyone may answer, please.
1, 5, 9.
Yes. Which color? 1, 5, 9, and 13. So we are using the blue color for it. Okay. So all the blocks 1, 5, 9, and 13. And similarly, 2, 6, 10, and 14 will be mapped to set 2. Okay. How can we compute this mapping? And this is, this is okay. There are different methods to compute this mapping. So I will now go with method number 1 and method number 2. Okay. It's all division. It's all division. Okay. Can you see here? Now there are 4 sets. What is the index for set 0? Anyone tell me what is the index for set 0? Anyone may answer. Yes. What is the index for set 0?
0,
0, 0. What is the index for set 1? 0, 1. The index for set 2 is 1, 0. And the index for set 3 is 1, 1. Okay. Can you see here? One way to figure out which set a particular memory address should go is to use the mod operator. There are 2 methods, and I will explain this with 2 methods. Okay. Now, if the cache contains 2 cache sets, now in this case there are 2 cache sets. Okay. So now what is 2k here? Now 2k is now there is, if we convert it, so 2 is for 2 is actually 4. This is I mod 2k. Okay. Now, for instance, which main memory blocks are mapped to set 2? Can you tell me which main memory blocks are mapped to set 2? In this particular example, the block 2, block 6, block 10, and block 14 are mapped to set 2. But how do we know that this block 6 is now mapping to set number 2? So we can use the mob operator. So how can the formula is actually I? What is I now? I is now 6. And 2k, what is now 2k? 2k is 4. So 6 mod 4. This is the remainder operator. So if we divide this 6 with 4, the remainder is 2. Okay. Again, now we want to find. So this block is now mapped to set 2. So you can use the mod operator. Okay. What about block 14? Now let's assume this is my block 14. Block 14. How can we compute it? 14 in percent operator of 4, it will give us 2. So if we divide this 14 with 4, so the quotient is 3 and the remainder is 2. So now this is the remainder operator. So the remainder is 2. So it means it's also mapped to set number 2. Any question? Any question? Got it or not got it? So this is method number 1. So the method number 1, what is I now? I is now the block address. I is now the block address. And what is K? K is actually the index field of the main memory byte address. Any question? Any question? Yes, sir. Is it clear?
Clear.
Good, very good. Okay, now we'll go further. Okay, now please look at here. Now what we are going to do, this is method number 1. Now this is another method number 2, which is much efficient. Now we are converting all of these main memory block into block addresses. What will be the address of this 0? 0, 0, 0, 0. This address will be 0, 0, 0, 1. And what will be this address 1? It will be 1, 1, 1, 1. If we go to the next slide, so these are the block addresses. Any question? Any question? Okay, now please look at here. Which blocks are now mapped to set number 2? Which blocks are now mapped to set number 2? Can anyone help me? Which blocks are mapped to set number 2? Which blocks are mapped to set number 2?
2,
Anyone may
6,
answer?
10.
Yes, 2, 6, 10, and 14. Okay, these are 4 blocks. And if you look at here, accurate made. So with our 4 set cache, we would inspect the 2 least significant bits of the main memory. Again, now if you look at block number 14, what is its address? Its address is 1110. And if you look at the index field, can you see this index field? And this index field is now mapped to set 2. So it means 14 is now mapped to set number 2. And if you look at this index field, got it? And now can you see also the block 6? We can either use the mod operator or the least significant k bits of the main memory byte address. Got it or not got it? Any question? Any question?
Professor,
Yes, please
this
go
is
ahead.
only for direct cache?
This is for direct cache. This is done for direct cache. Okay, now even it can be for any type of cache. It can be for any kind of cache. It's not only for direct map cache, but since, because you know why I'm using direct cache, it is applicable for any type of cache. Any type of cache. Yes. Got it or not got it?
Yes.
Okay. So now if you look at here, taking the least significant 2 bits of the binary value is the same as computing that value of mod k. Okay. Now this is now very important. Now we're going to why we need to add text bits. Okay. Now here, now how many sets are there on the right hand side? How many sets are there? Can you tell me?
4.
4 sets. Okay. How many main memory blocks are there? How many main memory blocks are there? Please help me. Help me. I need your
16.
help. There are 16. Very good. There are 16 blocks. Okay. Which block are mapped to set number 0? Can you tell me which block? Please look at the red color. Which blocks are now being mapped to set number 0? Yes, anyone may answer.
0, 4, 8.
0, 4, 8, and 12.
Yes, very good, very good. I'm really happy now. Today I'm very happy because you know you're replying. Even I have a headache. My headache is now gone. Very good, thank you. So it means that now block 0, block 4, block 8, and block 12 are now mapped to set number 0. But only one of them can reside at a time because now A is 1. Only one of them is now residing in the car. Okay, which block is now currently residing in set number 0? Which block is now currently residing in set number 0? Can you tell me?
Block 0.
Now in set number 0. Now please look at the data field.
Okay, wait. Oh yeah, so block 8. Block 8.
Block 8 is now residing in set number 0. Okay, now which block is currently residing in set number 1? We assume which block is now residing in set number 1?
13.
Block 13. And which block is now currently residing in set number 2?
6.
Block 6. And which block is currently residing in set number 3? Block 7. So actually, can you see here now? This is okay. Okay. Which block can be mapped here? The block here can be mapped here. It is actually 2, 6, 10, and 14, but only one is now residing. Okay. Now, how do we know that the tag field? Okay. What will be the, let's assume this block is now residing into is set number 0. What will be the tag field for this block? Can you tell me? What will the tag field for B8? Can you tell me? What will the tag field for B8? Anyone may answer. For the first line, for the first set, what will be the tag field?
1, 0.
Very good. Because this block 8 is mapped here and now it's 1, 0. Any question? This is clear or not clear? Okay. Now, second, Now we assume that now this block 13 is now residing in set number 1. What will be its tag field? Anyone may answer? Anyone may answer. What will be the tag field?
1 1.
1 1. And we assume that now this block 6, we assume that now block 6 is currently residing in the cache. What will be the tag field now? Can anyone help me?
0 1.
Very good. Thank you. Thank you. I'm very happy today. I'm very happy today. Okay, and now block 7 is, we assume that block 7 is currently residing in the cache. What will be the tag field now?
0 1 again.
0 again. Very good. Very good. This is very good. Good. Okay, now again, assume now that this is very important. Now I'm conversing the data. Let's assume we have a cache and we don't know which block is now residing. We don't know which block is residing in the cache. So let's assume we are now in set number 0. Assume that we are now in set number 0. We are now in set number 0 and the tag field is 10. So what will be the main memory block address? So this is the tag field and this is now the index field. So can you see here? Now, please remember, now the index field is now 0 0 and the tag field is 10. So if we concatenate the tag field and the index field, it will give me the main memory block address. So now looking into the data, can anyone tell me which block is now residing in set number 0? Anyone may tell me which block is now residing in set number 0? Now the tag. So the main memory block address can be determined by concatenating the tag field and the index field. So can you see here now? Here the index field is 0 0, the index field is 0 0, and the tag field is 10. Which block is residing in set number 0? Anyone may answer. Help me.
4.
Which block?
Block 4.
Block 8. Why? Because if we have 1 0 0 0,
yes,
1 0 0 0, we cannot. Okay. Now again, which block is now currently residing in set number 1? Let's assume, looking at this data, which block will be currently residing in set number 1 now? Looking at this data.
13.
Very good. 13. And which block is now currently residing in set number 2?
6.
6. And which block is residing in set number 3?
7.
Help me. Yes. Any question? So now if we have, now the thing is, if we are giving us, and please remember, this may be the question in exam. So I will give you any scenario, and I will give you the set index field and the tag field, and you say, okay, I can ask a question. This may be the question in your midterm. This may be a question in your midterm because cache topic is now included in the midterm. Okay, I say, okay, I can give you the tag field, I can give you the index field, and I say, okay, which block is currently residing there, and then you need to tell me. Any question? Got it? I can change the number of sets, I can change the number of tag bits, I can change the number of, so I can change the number of blocks within the cache. Okay. Now, then one is more detailed. This is very important now. This is very, very important. And why I'm doing this? Because if you look at the tag field, so this is the tag field. Can anyone tell me which block is now residing in set 0? Can anyone tell me which block is now residing in set 0? Because now, can you see here? This is 1 0, and now this is 0 0. Which block is now residing in set number 0?
8.
Block 8. But block 8 is now residing in the cache. Which block is residing in set number 7? Block 7. What about this block? Which block is now residing in set number 1?
None.
None. It's invalid because the valid bit is 0. This is very important. And can you see, when the valid bit is 0, it means either the tag matches, since it means does not represent a valid data. So now it means that now in set number, in this particular example, if the valid bit is 0, it means that the block that is residing in the data field is now invalid. And can you see here now what we are going to do for the last tag? So what do? We concatenate the tag bits, which is actually 0 1 and then 1 1. It means that block 7 is now residing. So in this example, block 8 is now residing in set 0. Block 7 is now residing in set number 3, and set number 1 and set number 2 does not contain a valid data, though there has the set tag field. Any question?
Professor, just one.
Yes, please go ahead.
So let's say this was valid, the places where the valid bit is 0.
Yeah.
And if it was valid, then would it be the same
Yeah.
block
Yeah, the
over
same
there?
thing as we did in the previous thing. So if it will be the tag field, it is actually 110, and it means that block 13 would have been resided here, and then it will be 0110. It means that block 6 would have been resided here if the valid bit is 1. So for the previous example, we assumed that all of the valid bits are here are 1. Got it or not got it?
Yeah.
I hope I answered your question now.
Yeah, now it did.
So now in this particular example, we assume that all the valid bits are 1 here. But in this here, example, it means we make some of the interest to be invalid. Any question?
No, not anymore. Thank you, Professor.
Okay. Now what is now the problem with the direct map cache? Okay. Now I will go. Now we'll go to a direct map cache. Okay. And there are some timelines. This is now a direct map cache, and there are some timelines. Okay. So now initially this is now the address. Now this address is now at time 0. This is time 1, time 2, time 3, time 4. Okay. Initially we want to access the main memory block 0. This is main memory block 0. So the tag bit is 00 and 00. It means that we are accessing block 0. Okay. This is 000. It means that it is block 0. Okay. This address, where this address will go? Anyone will tell me? Can anyone tell me where this address will go? Can anyone tell me? Please help me.
Which address?
Yes, this is block 0 now. Can you see? This is now my block 0 now.
Yes.
It will go to which set? Set 0. It will go to set.
Yeah, 0.
It will go to set because the index field is now 00. Since the index field is 00, it will go to set 0. Okay. So now can you see here? So now this is actually, it will be initially hit or miss initially.
Should be a hit though.
No, it will be miss. No, because you know because the tag field is now 0. So initially this is a miss. So can you see here? Now we put we set the value bit to be 1, and the tag field is stored here now. Can you see here? Now the tag field is stored here. Any question? Any question? Got it or not got it?
Yeah, got it.
Now, if you go to the next line, in the next iteration, at next time, let's say in future, we want to access block number 1. Can you see? This is now block number 1. To which set it is mapped? Can you tell me to which set it is mapped? Anyone may help?
0.
Anyone may help, please. No.
1.
No. Yes, why 1? Because we look into the index field. It will go to the index field. Okay, when we go to the index field, now it will be mapped to set number 1. It will be a hit or a miss. Anyone may answer.
Hit, because the tag was already in 00. You already went before.
No. Can you see now? There is a right. Now there's why that's the reason that I included this thing. So this is main memory block 1. Please remember, main memory block 0 is mapped to set number 0. Main memory block 1 is mapped to set number 1. Why? Because this is set number 1. So can you see here? Its tag is 00. So can you see here? Now this is a miss. So now memory block 1 is now mapped to set number 1. Any question? Yasir, I hope I answered your question.
Yes, now it's clear.
Now it's clear? Okay. Now in the next iteration. Okay. Now at this point of time now, we have 2 blocks in main memory. Sorry. We have 2 blocks in cache. Main memory block 0 is now residing in set 0. Block 1 is now residing in what? Set number 1. We want to access block 2. Where it will go? Can anyone tell me?
Set 2.
Anyone may help?
Set 2.
Set 2. Why set 2? Why set 2? Why not set 5? Why not set 6?
The index.
Because the index is 10, so it will go to them. So can you see here? Okay, now it will go and it will go to the, it's a miss. So this main memory block 2 will be mapped to set 2, and the tag field is now 00. Any question? Any question? Okay. Again, we want to now access the main memory block 3. Okay, and 3 blocks are currently now residing in the cache. 3 blocks are currently residing in the cache. What should you do now? Help me. Anyone help me? Anyone? To which set is it mapped now? Anyone may help?
Professor, why did it miss in set 2? If there was already in 00? Or was it empty before?
But it was empty before because you didn't look into the animation now.
Okay. I thought it was.
Okay. Now please, and now at this point of time, we have already 3 blocks: mem0, mem1, and mem2. And then you'll say, oh, it's a hit. It's not a hit now. This block 3. Okay, please remember, we are accessing block 2 for the first time, not for the second time. Please remember, since we are accessing it for the first time, it will be always a miss. I hope I answered your
Yes,
question.
I thought it was. Yeah, I thought it was already.
No, it was not there. It was not
Yeah.
there. So can you see here now we want to access memory block 3. It is mapped to set number 3. So it will go here. It will go here. What will be the tag field? Okay, this memory block 3 will mapped here. Got it or not got it? Any question? And they will miss. Okay, now the next iteration. We want to access main memory block 4. To which set it is mapped? Anyone?
Set 0.
Set 0. It will be a hit or a miss?
Hit. Should be hit if you already.
No. Because can you see here? This block 4 is now mapped to set number 0. So this is mapped to set number 0 here.
But it has different tag, Professor. So.
Now we have a different tag. Very good. Now this. Yeah, I really like it. My headache is now gone. Can you see here now? We look into the index field, and then we compare this tag with this tag. Does the tag matches or in matches? Doesn't matches. Anyone may answer.
It doesn't match, so it will replace it, I think. No?
It will replace it. Very good. I really like it. So it will replace it. So can you see it's a miss? It will replace it. So now we bring block 4 from the main memory and we kick out block number 0. And it's a miss. Okay. Now in the next iteration. Now at this point of time, block 4 is now residing in set 0. Block 1 is now residing in set 1. Block 2 is now residing in set 2. Block 3 is now residing in set 3. And now we have 3. To which set it is mapped? It is now mapped to set number 3. And then we compare this tag with this tag. Yes. Hit or miss? Anyone may answer.
Hit.
Can you see? Please remember, we bring it for the first time. So we push it in set 3 and now we are referencing it again. So this is actually now the temporal locality. So now this is not a temporal locality. This is the temporal. We are accessing the same item again. So now it is a temporal locality. We are accessing the same item again. And this is any question? Should we proceed? In the next iteration, now please look at here. In the next iteration, now we have block number 4. Block number 4 is now residing. And okay, this block number 4 is now mapped to set number 0, and then we compare the tag field. This tag 01 and tag. It's a hit or a miss here. Anyone may answer. Hit. And now we want to access block number 15. Now if you want to access block number 15. Okay, now if you convert this 15 into binary, it is actually 1, 1, 1, 1. To which index it is mapped? To which set it is mapped? Anyone may answer. Which set?
3.
Set 3. And then we compare the tag field. What is the tag of the incoming block? The tag is 1, 1.
And
they are different. What we need to do? Kick who?
Replace.
Replace what? 4, 1, 2, or 3? Should I replace 4, 1, block 2, block 1, block 4, or block 3?
Block 3.
And now the tag field is updated. Now the tag field is updated to 1, 1. Any question?
Professor?
Yes, please go ahead.
At the first couple of iterations, will we always miss or not necessarily? Only in this?
It will always be a miss because initially, whenever the cache is started, when you start up the system, so all the valid bit will be set to 0 initially. Please remember, whenever you start up a cache, all the valid bit will be set to 0 on the startup. Any question? I hope I answered your question.
What if we have the same tag twice in the first 2 iterations? Then it will hit, right? It's fine.
Yeah,
That
yeah,
should happen.
definitely will hit. Yes, yes, it will. If you did the same take and the same take and the take field is okay. Now, please remember there are two different things. It's not about same tag. It has go to the particular set and then compare the tag. Please remember, can you see here? Now, can you see this tag is also 0, 0, this tag is also 0, 0. But this tag is for set 0 and this tag is for set 1. So first we need to know which particular main memory block is mapped to a particular set. Any question? I hope I answered your question. Yes, Yasir.
You did,
Yasir,
Professor. Thank you.
this one? What?
It's clear.
It's clear? Good. Good. Okay, now what is the problem with the direct map cache? Okay, the same thing. We have the same the same example now. Let's assume there are 16 memory blocks and there are 4 sets. Okay, now block 0 and block 4 are all mapped to the same set now. Got it? So block 0 is also mapped to the same set. Block 1 is mapped to set 1. Block 2 is mapped to set 2. Block 3 is mapped to set 3. And block 4 is again mapped to set 0. So now when we access 0, it will be a miss. So we bring block 0. In the next iteration, block 0 is currently residing. It's a miss. We kick this out and then we bring block 4. In the next iteration, we are again accessing 0. It will kick out. It will kick out. 4 will kick out 0, and now 0 will kick out 4, and this goes on. So there will be all requests and all misses. Okay, now please remember, this is the problem that is with the direct map cache. In the direct map cache, this is called as the conflict misses. In this example, now first we access 0, then we access 4, then we access 0, then we access 4, then 0, 4, and blah blah blah, and so forth, so on. And please, even set 1, set 2, and set 3 are empty, but still it will result in a mess. Why? Because this is called as conflict miss. Any question? Even in this example, even set 1, set 2, and set 3 are empty, but if two blocks which are mapped to the same set and we are repeating it again and again, it will kick out each other. Any question? Any question?
Professor, if you have like 0, 4, 8, 12, it will be the same thing?
Yes, you do the same thing. Yes. If all the blocks which are mapped to the same set, and let's say if we want to have 0, then 4, then 8, then 12, and then again 0, 4, and 12, and add, and it always result in a miss. But if we have 0, 4, 4, so 0, 4, 4, then it will be a hit. After 4, it will be a hit if you repeat 4 again. I hope I answered your question. Yes?
Yes, it's clear.
Any question? Should we proceed?
Yes, Professor.
Okay. Now there is a problem now. Okay, this is our problem. Consider a main memory of capacity 1 gigabyte, which is byte addressable. We have direct map cache of 4 MB with 64 bytes per line. How many blocks are there in memory? How many lines are there in the cache? And find out the format of the main memory block address. Yes. Now, please remember, what is the memory size? Yes, can you tell me what is now the memory size? Please remember, what is A now? Anyone may answer. Please answer me. What is A now here?
Is it
Can
1?
you tell me? What is A? A is general. What is A?
The lines?
Address lines or data lines?
Address.
Okay, and what is D?
Data line?
Very good. Not D is a data line. Okay. Can you see here? Now, what is my memory size here now? What is my memory size here? It's given
1 gigabyte.
1 gigabytes. Okay, we need to find A because it is byte addressable. We need to find A. So can you see here? So can you see what is G now? Giga is actually G. So this is actually 2 to the power 30 multiplied by, and since it is byte addressable, so I will say 8, and this 8 and this 8 will cancel out. Okay. Now, what is now the address line width now in this case? Can you tell me what is the address line width? How many bits are required for the address?
30.
30 bits. Okay, how many bytes are there in main memory? Can anyone tell me how many bytes are there in main memory now? Anyone may answer. How many bytes are there in main memory now? It's given. So there will be 2 to the power 30 bytes in main memory. Okay, now can you see here? Now this is my main memory block address. Okay, the main memory byte address. Now this is my main memory byte address, not the block address. Sorry, this is a small mistake. So I call this as the main memory byte address. Can you see it? This is the main memory byte address. Okay, now this is the main memory byte address. Okay, it consists of, please remember, it consists of 3 fields. One is the T stands for tag bits, K stands for index field, and B, which is the byte bits. And we already did it. Okay, okay. How many main memory blocks will be there in memory? Can anyone tell me? If you want to compute n, that we want to compute the number of blocks in main memory. Yes. How can we compute the number of blocks in memory? Can anyone tell me? How many total blocks will
2
be
to
there
the
in main
power
memory?
30 divided by 2 to the power of b.
Yeah, very good, very good. So the number of memory blocks, it is actually the number of memory block will be the memory size. The memory size is 1 gigabyte, and the block size is now 64 bytes. How many blocks will be there? The memory size is now 1 gigabytes. 1 gigabyte is now here. This is now my 1 gigabyte, and the block size is now 64 bytes. This is now 64 bytes. And if you calculate the number of n, so it is actually 2 to the power 30b divided by 64b. What is 2 to the power 30b? And b will cancel out. So how many blocks will be there in main memory? 2 to the power 24 blocks will be there in main memory. Any question? Any question? And if you change the block size, so the number of blocks will change. Any question? Should we proceed?
Yes.
Okay. Okay. How many bytes will be required? How many? What is B now? Can anyone calculate B? Can anyone tell me B? What will it be
6.
now? Very good. 6, because 2 to the power 6. So this is 6. Okay. Now, so it means that if you compute this, it means that there will be now 167777216 blocks. So there will be these number of blocks in main memory. Okay, now we want to calculate the number of lines in a cache, the total number of lines. Please remember, it is the total number of lines in the cache. And what is the total number of lines in the cache? It is actually S multiplied by A. So the total number of lines in the cache is actually calculated as the cache size. The cache size. What is now the cache size here now? The cache size is actually 4 MB. And divided by the block or the line size, which is our 64 byte. And if you do that, so it is actually, what is L now? L is actually 4 multiplied by 2 to the power 20 bytes and divided by 64 bytes. This is actually, what is 4? 4 is actually 2 to the power 2, and this is 2 to the power 20. And then divided by block size, which is 2 to the power 6. What is now L? So if you compute L, so this will be, it is actually 2 to the power 22 divided by 2 to the power 6. So how many lines are, total lines are there in the cache? And can you tell me how many lines are there in the cache? There are 65,536 cache lines. And what is now the block size? The block size is actually 2B bytes per line. It is actually 64 bytes per line. So can you see it is actually 2 to the power 6. And can you see here now what is now B? B is now 2 to the power 6. So B is now 6. Any question? Any question? Should we proceed? If there is any question, please let me know. Any question? Yes, yes, sir.
Clear.
Clear. Okay, now, so this is B is now 6. We have computed B. Okay, what is A? A is now, please remember, A is 1 for direct map cache. And how many number of lines are there? What is the total number of lines? The total number of lines is actually S multiplied by A. So how can we compute S? S is equal to L divided by A, and we computed L here. L is the total number of lines, which is actually 65,536 divided by 1. So what is K? K is actually log 2 of S. So K is actually log 2 of 65,536, which is actually, how many bits are required for the index field? Anyone? 16. Okay. Now, how many bits will be required for the tag field? Can you tell me? Yes. Looking into the figure. What is A now? A is actually T plus K plus B What is now T? Can anyone compute T? Yes. How can we compute
30,
T?
30 minus 16 minus 6.
13 minus 16 minus 6, which is actually 8. Any question? Should we proceed?
Yes.
Should we proceed? Please now. Okay. Please now. This is another problem. This is another problem. Please can you try this problem on your own? Can you try this problem on your own? Okay. Now what is the memory size? The memory size is now 2 to the power A cross D. What should I put on the left hand side? Yes, what should I put on the left hand side? Anyone help me? What should I put on the left hand side?
256 megabyte.
256 MB. And then it is actually 2 to the power A, and it is, since it is byte addressable, so D is 8. So can you see 2 to the power 56 MB is equal to 2 to the power A multiplied by 8. And if you go to, what is 256 now? Can you solve it? What is this 256 now? Help me. It is actually 2 to the power 8. And what is M? 2 to the power 20. B is 8. So 2 to the power 8, it is actually 256. What is M? It's 2 to the power 20, and B is actually 8. And it's 8 and 8 will cancel out. What is now A? Can you now tell me what will be the value of A now? Anyone may answer. What is the value of A? It is simple math. Anyone may answer. Yes, Yasir. What should be A now?
Is it 28?
Yes, it is 28. Yes. Very good. It is 28. Very good. Okay, now we have this A, main memory block address. So this is actually not 25 bits. We need to find D, we need to find K, and we need to find T. Okay, now we need to find the number of main memory blocks. How many main memory blocks will be there? Can you now tell me what will be the formula? The main memory blocks here. Help me. It is what? Help me.
2 to the power B.
No. The number of blocks in main memory. No. It is actually the number of blocks in memory can be calculated by dividing the memory size with the
yes,
block size.
The size with the block
What?
size.
Yes. What is the memory size here now? 256 MB divided by the block size, which is actually 32 byte. And if you calculate it, so it is actually 2 to the power 8 M, it is 2 to the power 28 byte divided by 32 byte, and we cancel out each other. So this, how many blocks will be there in memory? So there will be 223 blocks. This will be 8388608. So there will be 838608 blocks in memory. Any question? How many lines are there in the cache? Can you tell me? Can you tell me the formula? How can we compute L? It is calculated, the number of lines is calculated by dividing the cache size. Okay, the number of blocks in main memory can be calculated by dividing the main memory size by the block size, and the number of lines in a cache can be calculated by dividing the cache size with the block size. So now what's the cache size and the block size? So the cache size is 1 MB and the block size in this example is 32 byte. So can we see here? So now when we solve it, so what is L? L is now 32,768 cache lines. Okay, please remember, if these are the total number of lines, the total number of lines in a set, in a cache. Okay, how can we compute L? L is equal to S multiplied by A. What is S now? Can you tell me what is S now? Help me. What is S? Anyone may answer. L is equal to S multiplied by A.
L divided by A.
No. What is L? L is actually S multiplied by A. Okay. So now can you see? And the associativity. So can you see the block size? The block size is now 2 to the power B bytes What is now the block size? The block size is 32 bytes, so this is actually 32 bytes. This is actually true for 5. How many bits will be required for B? So for B, we need 5 bits. And then what is A now? A is for 4-way associated, this we have A is 4. How many number of sets are there? So the number of sets are actually L divided by A. What is L? L is equal to S multiplied by A. So this is 32,768 divided by 4. It is actually 8192. And if you go there, so what is K? K is log 2S, which is actually how many bits will be required for the index fields, and this field is 13 bits. And now we compute T is equal to this, so now we have 10 bits. Got it or not got it? Any question? Any question?
It's clear.
Is it clear? Okay. Now what I'm going to do, so now I'm now solving another question. So now I'm now solving another question, and then I will solve it. So this is like, these are the question already with the lecture slides, and I'm now solving another questions. Okay. So now I'm solving another question. 1 minute. I'm solving another question, and I will solve it like, in a very. It's a different question now. Is it visible to you or not? Screen visible to you? Yes or no?
No, Professor.
No.
No.
Why? It's not visible now?
No, still.
Okay, maybe when I plug in my writing pad, so this causes a problem. I don't know why. Why it's. I'm again sharing it. Is it visible now?
Now it is.
Okay, good. So now solve another question. Okay, so let's assume we have an 8-way associative cache. Okay, and let's assume the size of the main memory is, assume that it is actually 32 gigabyte. Okay, and then we have an 8-way cache. 8-way cache, and then we have the cache size is, let's assume 4 MB, and let's assume we have 128 byte per lines. Okay, so now we are going to solve this question. Got it or not got it? Any questions? So now we're going to do copy, and then what I'm going to do, as you know, I will make it again and again and again and again. Okay. Now, is the screen visible to you, everyone? Yes or no?
Yes, yes.
Okay, now we are going to solve this problem. So first, what is my main memory now? So now what is my main memory? Size is actually truth for A cross D. What is my main memory size? It is actually 32 gigabyte, and this is actually truth for A cross D, which is, since it is byte addressable, we call it 8. So what is now this 32? So please remember, this 32 is now truth for 5, and now this gigabyte. What is gigabyte? Can you tell me? Truth for 30, and now we have this byte, which is 8, which is actually cross 8 is equal to truth for A cross 8, and this 8 and this 8 will cancel out. Any question? Any question? So now what is, can you see here? So now actually we have 5 plus 30, which is actually truth for 35, which is actually now truth for A. And what is now A? A is now 35 bits. Any question? Okay, now what we do partition this main memory block address into 3 fields. These are 3 fields. So now this is my A. A is now 35 bits. It can be partitioned into 3 fields, namely the tag field, which is T. Then we have the index field, which is actually K. And now we have the byte field, which is actually B. And if we compute T, so what is T? T is actually what? Sorry. If we compute A, what is A? A is actually T plus K plus B. This is clear or not clear? Anyone? Clear or not clear?
Clear.
Okay, now we need to, okay, now please remember, we need to compute B. We need to compute B. So let's say we need to compute B. What is B? B is actually log 2 of the block size. Got it? So now if we look at here, so it is actually log 2. What is my block size here? Can you tell me? What is my block size here?
128.
Yes, 128. So this is actually log 2 of 2 to the power 7. And what is now B here? Help me.
7.
7. So now how many bits will be required for B? So B is now. Any question? Any question? Clear or not clear? If this is not clear, I will not proceed further.
It's clear, clear.
Yes. Okay. Now this is my block size. Okay. Now if you look at here, this is my block size now. Okay. Now we go to there. Why we need to find n? Please remember. Now we need to find n. What is n? N is the number of main memory blocks, and it can be determined by the main memory size divided by the block size. What is the main memory size here? Help me. What is the main memory size?
2 to the power 35.
32 gigabyte divided by the block size. Now we have the block size. So now I can use green color for this. So the block size. Now this is my block size. So the block size is 128 byte per line. So 128. Okay, byte. So can we see here? So this is actually, can you see here? Now I can use the green color. So this is 2 to the power 5, 2 to the power 30 B divided by. Okay, so now this is my one thing, and now we want to compute this with the 128. What is 128? Is actually 2 to the power 7 B. Okay, and now if you look at here, so now this B and B will cancel out, and this is actually equal to, now if we go there, so this is actually 2 to the power 35 divided by 2 to the power 7, and 2 to the power 35 divided by 2 to the 7 is actually what? So this is actually 37. It is actually what? Help me. 2 to the power what? 28. So how many memory blocks there? So there will be 228 memory blocks. Okay, can we see here? So now please remember, this is very important. This is very important. Now if you go to the memory map, now this is my memory map. So now please remember, so now this is my main memory block 0. Now we have main memory block 1 and blah 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 blah. What will be the last block? Can you tell me? Help me. Main memory block what? Help me.
2 to the power 28 minus 1.
Minus 1. Please remember, so this how many memory blocks here? So these are, if you go for here, so these are how many? Please, these are 2 to the power 28 main memory blocks. Okay, now this is very important. Now what I'm going to do, so now I'm going to copy, and then I'm making it paste spatial, because you know I want to do a lot of stuff here. Now I want to do a lot of stuff here. What I'm going to do now, please look at here. So now look here. So this is actually what I'm going to do. I'm copying it here and I'm pasting it here. Okay, now if you look at here, okay, now how many bytes are there in main memory? Please remember, how many bytes are there in memory? There are 2 to the power 35 bytes in main memory. So how many bytes are there in memory? So can you see here? There are 2 to the power 35 bytes in main memory, and we did it here. So can you see here? This is A, because it's byte addressable, so it is actually 2 to the power 35. So there are 2 to the power. So can you see here? Now from here we can say, just draw, yeah. So this, it means how many bytes are there in main memory? So there are 2 to the power 35 bytes in main memory. So if there are 2 to the power 35 bytes in main memory, so now how will that work here? So now if you go from the byte size, so this will actually, can you see here? This is actually byte 0, then byte 1, and blah 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 until, and then this is actually byte number 127. Why 127? Okay, and blah blah blah. What will be the second byte? Can you tell me? Like, then it will be byte 128 and blah 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 blah, and what will be the last byte? Can you tell me the last byte? The last byte, help me. Byte number what?
2
Truth
power
power?
55 minus 1.
Minus 1. Okay, please remember. Now this thing belongs to which main memory block? Can you tell me?
Is it set 0?
No, main memory block 0. This is now main memory block
Oh.
0. And now this one. Can you tell me? Main memory block 1.
1.
Okay, now can you see here? Now this main memory block 0. Now this main memory block 0 will consist all of the bytes from byte 0 till byte 127. Any question? Not 128, 127. And what about main memory block 1? Can you tell me? Main memory block 1. What will it contain? Anyone help me?
128
128 till 255.
255.
Yes. Let's assume we have another main blocks. Let's assume main memory block 2. So the main memory block 2 will start from where? Help me.
256.
To 383 and so forth. And if you look at the last memory block, this will now contain all the main memory blocks from main memory byte 235 minus 1 till you subtract 64 from here. Got it?
28.
Yes, and then main memory block 2 spot 35 minus 1 minus, because can you see here? So what we do? So we minus 127. Any question? Clear or not clear? This is very tricky, and then you can do this.
Professor, you said the number of blocks is 2 to the power 28?
Yeah, but now this block, yes, it is 2 to the power 28. Yes, but it will contain not the main memory block. It is actually byte number. Because can you see? It will contain this block will belong here. I hope I answered your question.
Yes,
Yes.
the bytes are inside the memory blocks.
Yeah, the byte. It is the byte inside them. Got it or not got it?
Yes.
I hope I answered the question. Okay. Now we have the same question. Now we have computed. Now we have all these things. We did this, and now what we are going to do? We are now computing the number of lines. Now we are computing the number of lines. The number of lines is actually the total number of lines is actually the cache size divided by the block size. What is the cache size? So the cache, we have 4 MB cache. Yeah, 4 MB divided by the block size, and the block size is 128 byte. So this is actually 2 to the power 2, and this is 2 to the power 20. This is B. Then it is actually 2 to the power 7 and B. And can you see here? This B and B will cancel out each other. So this is actually 2 to the power 22 divided by 2 to the power 7. This is actually 2 to the power 15, and this 2 to the power 16 is actually there are 32,768 sets. And if you look at this line, sorry, total number of lines. Got it or not got it? Any question? Okay, now if we go here, so now if we solve it further, I know everything, everyone will kill me now. I don't know if even I make one even I'm delayed, you people will kill me. I know that. Okay, so now we have, what is now my total number? L is actually S multiplied by A. The total number of lines is equal to S multiplied by A. What is L here now? L is actually 32,768 is equal to S. S is now, we need to find S, and now we can see here what is now A here. So please look at here. What is A here now? A. So A is 8. A. So A is 8. So A is 8. What is now S? S is equal to 32,768 divided by 8. So how many sets are there? Can you see here? So this is actually 2 to the power 15 divided by 8.
4096.
So this is actually 16,4096. So this will be 4096 sets. If there are 4096 sets, so we will have set 0, set 1, set 2, and until set number 4095, and each set consists of how many ways? So each set will consist of way 0, way 1, way 2 until way 7. There will be 7a, and for these we have valid bit and tag bits and blah blah blah. So now can you see here, now what is now s? So what will be now k? K is actually log 2 of s. What is s now? S, can you see here, what is s now? So this, if you compute this 4096 towards for 12. So what is s? K is actually log 2 of s. This is actually log 2 of 2 square 12, and k is now 12. So k is now 12. So please remember, we found what is b. What is b? B was 7. What is now k now? Help me. K is now, and then the total is now 35. So 35 minus 12 minus 7. So these are not take bits. Any question? Okay, so we will do some more examples in my next lecture. So I'm going to do, and I'm going to finish it now, because if I do not finish, you people will kill me. So I want to be alive. So what I'm going to do, I'm now